Hello everyone, let's go back to separable ODEs. This time let's work out initial value problems. This time you really have to focus on the intervals of definition. Let's begin with something relatively simple. Let's go to problem 1a. In this case, dy dt is equal to y, and let's solve it. 1 of y dy is equal to dt, isn't it? Am I doing this right? From here. Okay, alright. Let's take the antiderivatives. Log of y is equal to t plus c, so y is equal to e to the t plus c. But we can separate it, right? E to the t power times e to the c power, and consequently we are going to get some constant times e to the t power like this. Now, please recall the final form here is perfectly okay when negative y is coming here. When y is negative, then we need negative sign here. So basically, what we end up having is plus or minus here. And then, therefore, this is going to be either plus or minus. That's going to be either plus or minus. But then again, by taking this k as either plus or minus, we can absorb everything. So we have the general solution like this. Please remember this trick. We talked about this in great detail in the previous video. Alright? Okay, we have the general solution, alright? Now let's consider the initial conditions. Alright, first initial condition. When y is positive, so what do we have? Y is equal to k e to the t power, but y of 0 is k times e to the 0 power, that's 3. K is 3, consequently, y of t is 3 e to the t power. That's blue. Okay, how about red? Y is equal to k times e to the t power. Y of 1 is negative 2. K times e to the 1 power is negative 2. Therefore, k is negative 2 over e. Therefore, y of t is, let's say, negative 2 over e times e to the t power. Is that it? I don't like this expression very much. E in downstairs, let me rewrite it as e to the negative first power. Excuse me. So downstairs is okay, but it's better this way. It looks easier this way. Alright, now we'll have better form. Negative 2 times e to the t minus 1 power. Previous expression I had with e in denominator is perfectly okay, but this one looks better. Those are two solutions. And this time, we didn't have to worry too much about those intervals of definitions and stuff because we already did. Remember, in the previous video, we went a great detail about how to deal with this logarithm, and eventually we ended up with this separation and coefficient times exponential, where coefficient can become negative and solve everything. We took care of it already, and that's why these two problems became simple. All right? Okay, all right, we got these two. And by the way, how about some visualization? Well, here we go. And we have those direction flows. And then we are following the direction flows. And we have those gray curves. Those are part of the general solutions. And then among those solutions, we are looking for those particular solutions that goes through the initial condition, and this one 0, 3, and this one 1, -2. Okay, that was quick, but then again, that was quick because we already took care of it. This one is not going to be that simple, and let's go. Well, I take it back. It's not going to be that bad. It's not going to be that bad. As a matter of fact, we already saw this example in previous lessons, so I hope everybody remembers at least part of it. Anyway, let's solve this. dy dt plus 2ty squared is equal to 0, but we want separation of variables, so flip this one over to the other side and then write like this. Okay, that was trivial manipulation. And then we take the separation of variables. All the y's to the left, all the t's to the right. So 1 over y squared dy, oh, I need some space here. And dy should be upstairs. Is equals to -2t dt. This is okay, but I don't like this 1 over y squared. If you take the antiderivative with this, this may cause some confusion and cause mistake. Here, it may give you an illusion this is a reciprocal function and you may be thinking about logarithm. But no, this is not reciprocal function. It is a power function. Now let's take the antiderivative, y to the negative first power, add 1 to the power, and divide. Minus and then t squared plus c. Does it look okay? One over -1, that's actually just negative. Therefore, I'm having 1 over y equals to t squared minus c. Did I get it? Running out of space, so let me continue there. So 1 over y equals to t squared minus c by multiplying -1 to each term. Therefore, y is equal to 1 over t squared minus c, and looks like I have a general solution here. Okay. Nothing bad happened when I took the antiderivative here, but did it really? Well, let me give you a brief reminder here. in the preliminaries. Some students may not remember because they skipped. But let's see, if you go over to this topic here, piecewise differentiation, believe it or not, the given calculation is wrong, correct it. Antiderivative of 1 over x, log of absolute value plus c. What's the problem there? And what's the problem there? Problem was singularity. Log, we have log of x or log of negative x. We can have two different constants there because these two intervals are unrelated. And for this, again, we have two different antiderivatives, and we may have two different integral constants because these two intervals are unrelated. So we may have separate intervals of definitions there. Let's come back to this. Are we in similar kind of situation? We have denominators, so yes, we are in trouble, to tell the truth. But let's forget about the trouble and let's just go ahead and do this. Okay, all right. Y is equal to 1 over t squared minus c, and over there I'm going to plug in y of 0 equals to negative 1 is equal to 1 over 0 squared so minus c is equal to negative 1 c and 1. Therefore, y of t is equal to 1 over x t squared minus 1 here. Did everything done okay? Was everything done okay as far as this is concerned? How about the next initial condition here? Well, let's do something similar. Y equals 1 over t squared minus 1. Therefore, y of 2 is 1 over 2 squared minus c. That should be 1/3. So 1 over 4 minus c is equal to 1/3. What do you get? C equals to 1, right? That's what I get from the second initial condition. How about the third initial condition highlighted in green? I have a feeling we may get something similar. Minus c here, minus c here. Y of negative 3/2 is 1 over negative 3/2 squared minus c, and that's equal to 4/5. So 1 over 9/5, 9/4 equals 4/5. I was affected by this 5 here. 3 squared is 9, 2 squared is 4. And then if I simplify, I'm going to get 4 over 9 minus 4c by multiplying 4 to each term. And that's to remove this denominator here. And I'm going to get, you guessed it, c equals to 1. So that's for green condition. So what did you get? The same thing all over. So do we have the same solution for all these three problems? The answer is no, not really. The function part is correct. They are the same, but we have different intervals of definition. How do you see it, and more importantly, how do you anticipate it without seeing? Go back to the problem. We may have singularities here. Denominator may hit 0 and everything will just blow up from there. And that's what we have to avoid. And this is the visualization. We have those arrows there, direction field. And here we go. We have 3 initial conditions, and then we have 3 separate curves which are not affecting one another. So we have actually 3 completely different solutions here. The function part is the same, but we have 3 different intervals of definitions. And which is which, and how do we tell? Well, we have the same function, 1 over t squared minus 1, and 1 over t squared minus 1 is valid in the domain. Let's go back to college algebra days and try to find out the domain of this function. Set the denominator equal to 0, and we have to avoid those points, right? So negative infinity to minus 1, because that's when the denominator hits 0. And then union, negative 1 to positive 1, union, and then 1 to infinity. And then let's go back to these initial conditions. This blue condition, t equal to 0, came from here. And the red condition here, y of 2, so t equals to 2, came from the third interval. And then t equals negative 1.5 came from the first interval. So the proper answer here is these functions along with the intervals of definition, and let's go back to the notebook, and here they are. Correct function, but we'll need to specify the interval of definition. Correct function, but you need to specify the interval of definition. Same here again, same function, but different interval of definition. And they come eventually from the initial conditions. Why are they related that way? That is related to information flow, and that's a bit advanced story. But in any case, even without those, you can still find out those intervals of definition for each case. So what's the moral of the story? Separation of variable and finding out the solution, that's easy. Separation is easy. Calculating the antiderivative is easy. How about the interval of definition? How do you take care of those singularities? Now that's a problem. For logarithm, we will have some lengthy discussion in previous video, how to take care of those e to the something plus into coefficient, and that coefficient can be allowed to become negative, that idea. But for other cases, what can I say? Those are case by case, and you have to get your explicit solution and then look at those solutions carefully to find out any singularity or things like that. That's usually the best.